All right, howdy everybody. We're here to talk about Boyle's law, and we're talking about Charles' law and Guy-Lussac's law and the combined gas law, and we're going to just show the calculations here. If you want to know the theory, you need to refer back to the gas laws lab, where I'm talking about the graphical relationships and all those just up and down relationships. But remember, Boyle's law is with pressure and volume. Temperature remains constant, number of moles remains constant. So we remember that because we boil peas and vegetables. That's Boyle's law. Get it? Okay, so a gas has a volume of 7.40 liters at 765 millimeters of mercury and 25 degrees Celsius. What volume in liters will the gas occupy if the pressure is increased to 1,075 millimeters of mercury and the temperature remains constant? So temperature remains constant, we're going to exclude it. So first I'm going to kind of glean information that I already know. I'm going to get P1 and V1. And so my initial pressure was 765 millimeters of mercury. My initial volume was 7.40 liters. My second pressure was 1,075 millimeters of mercury, and my second volume is my unknown, right? So don't write that question mark, write an X, okay? You shouldn't write a question mark in your equations. So that's my unknown, that's my X. So I just take these numbers now that I've gotten some my known information and I know what I know what I don't know. I put these guys into the equation. So I'm going to plug them in. P1 is going to be 765. I'm going to go ahead and drop units because I know that I have 7 millimeters of mercury here and I have millimeters of mercury here. They will be the same, so that's fine. So that means that if I put liters in here, I'm going to get liters out. Okay. So 765 is my P1, and this guy is my V1, so that's 7.40. And then this is my P2, 1075, and this is my V2, that's my X. It's P1, V1, P2, V2. You see how that works? And so now, essentially, what you need to do is divide both sides by 1075. I shouldn't have written all those purple letters under there, but I need to divide both sides by 1075. What that will do is that will cancel these out, leave x all by itself, which is the way we like it. We like it lonely. So 765 times 7.4 divided by 1075. That's what you type in your calculator without the purple stuff, right? That's what you type in. And so that will give you your new x value of 5.27 liters because we should have 3 sig figs in our answer. We have 3 sig figs in our problem. That's the least number. We're not going to include that temperature because it was remained constant. It wasn't used in the calculations. All right, so that number 4, let's go ahead and try that. Pause it, try it on your own, and see how it works. So is that what you got? Now for this, this is a real shortcut. I have cut the units out and also cut uh, all the initial information out. Now, it's possible you can do this, but only for those that are very, very, very brave. Remember, this was your initial pressure. This was your initial volume, your second pressure, and your second volume. Those that are confident in math, you can do that. That would be fine, but I suggest that you really try to keep up with your units because remember, those units will sneak in there and mess you up. So watch out for that. You had atmospheres here, so you should get atmospheres out. You had liters here and liters here. If they didn't match up, if you had liters and milliliters, you would have to convert your units, okay, so that they would match up. So when we take a look at connecting Boyle's law to kinetic molecular theory, why does an increase in volume lead to a decrease in pressure? Well, remember, because pressure is force divided by area, right? So if you increase the volume, it will increase the area, right? So as this number gets bigger, this number will get smaller, okay? So the pressure will be reduced. That means there's not as many collisions per meter squared. So now let's check out Charles' law. Charles' law is a relationship between volume and temperature. So as you take the balloon, you can pour it with liquid nitrogen and you get something that is a all shriveled up balloon because it is a flexible container, right? That's how the pressure is able to remain constant if it's a flexible container. So very cool thing. Now, one really, really specific thing, I'm going to use the red pen for this one. This temperature always must be Kelvin. Okay, so the temperature must be Kelvin. So here's what you have to do for that. 0 degrees Celsius is equal to 273 Kelvin. So what you need to do for that is anytime you have any type of degree Celsius, like any X degrees Celsius, you will add 273 to make it its Kelvin temperature, whatever new Kelvin temperature is. So for example, if you had 25 degrees Celsius, room temperature, you add 273 to it, you will get 298 Kelvin. So you're feeling 298 degrees? No, 298 Kelvin right now. Okay, so it 298 may seem hot because it's kind of a high number, but it's actually room temperature. Remember, 0 Kelvin is the coldest you could ever get. So let's check it out. The Kelvin things are easy watch. A sample of gas has a volume of 150 milliliters when its temperature is 17 degrees Celsius. If the temperature is increased to 32 degrees Celsius, what will the volume become in milliliters, assuming the pressure remains constant? So you just take 150, divide by, and that's your initial volume, and your initial temperature is 17 degrees Celsius, and then you want your new volume, and then you get 32 degrees Celsius. Nope, can't happen. Remember, that is needs to be in Kelvin, so you need to add 273 to it. So a couple ways you can do this. I like to look at the problem, and as soon as I see degrees Celsius, I like to add 273 to it. So I'll take 17 and I'll add 273, and that's going to be 290. And then I'll take 32 and add 273, and that's going to be 305. So it's automatically done. So now 150 milliliters is my initial volume, and then 290 Kelvin is my initial temperature. My new volume is unknown, and we have 305 Kelvin here. So what you got to do is you need to multiply both sides by 305. That will cancel that out. And then so now what you do is you're typing your calculator. You can do it all in one line. Watch me do it. Take 305 times 150, and then we're going to divide by 290. Okay? Every time you see the multiply key, hit the times key, and then every time you hit divide, hit the divide key. As long as they're all multiplication and division, doesn't matter what order it's in. So we have 157 or 158. So your new volume is 158. milliliters. Let's go ahead and round that because it looks like the lowest numbers we had were 2 sig figs. So let's go ahead and round it to 160 milliliters. Okay? Go ahead and see if you can do the next one on your own. Don't forget to convert to Kelvin. Okay, you may have gotten there and gone, oh, I don't know what to do. All right. Well, um, sometimes having the variable in the denominator scares students, but check this out. All you have to do is take the inverse of both sides, which basically just means to flip them. So I'm going to put 298 Kelvin on top, 5 liters on bottom. And so I'm going to flip this one too. I'm going to put X on top and then 2 liters on bottom. Okay, so that's easy enough to do. Now you just have to multiply both sides by 2. And so 2 times 298 divided by 5 is going to be 119. So X is 119 Kelvin. And it asks me for what temperature in Celsius. So since it's in Celsius, I'm in Kelvin right now, I'm going to have to subtract 273 from it this time. And so 119 minus 273 is going to be negative 154 degrees Celsius. Very nice. So that's your answer. So if we connect Charles' law to kinetic molecular theory, why does an increase in temperature lead to an increase in volume? Well, increase in the temperature will increase the speed of the particles. Thus, in a flexible container, this will increase the volume. That will make the pressure remain constant. In a flexible container, make sure that you have to understand that the container must be flexible. Um, so, or no container. We talked about absolute zero before, so let's move on to Guy-Lussac's law. Guy-Lussac's law, same way, essentially the same type of thing as Charles' law. So we have pressure and you have temperature, let's just do the example. The gas in an aerosol can is uh, at a pressure of 1 atmosphere at 270 degrees Celsius. Go ahead and convert it to Kelvin. So we're going to add 273, so that's actually going to be 300 Kelvin. Ooh, that's nice. If the can is thrown into a fire, what is the internal pressure of the can in atmospheres when its temperature reaches 927? Add 273 to that, and you end up with 1200 Kelvin. Okay, so let's analyze that one. We got 1 atmosphere at the beginning, and then it was 300 Kelvin, slightly warmer than room temperature, right? And then we throw it into the fire or leave it in the middle of a hot car, and it gets up to 1200 Kelvin. Oh my goodness, that's warm. And so we need to know the new pressure. We're going to multiply both sides by 1200. Now check it out. You shouldn't need a calculator for that. Use your big brain. You've got 0, cancel out a 0 here, get a 0 here, we'll cancel out a 0 here. So now we end up with 12 divided by 3, which is 4, right? So 4 atmospheres is your answer. Okay? So the can all of a sudden gets to 4 atmospheres. That is actually a lot of pressure. That's why the can kablooey and explodes. That's why you never leave a hairspray can in your side of your car in the middle of the summer. So the reason why Guy-Lussac's law has an increase in temperature will lead to an increase in pressure, well, that's because remember pressure is force over area. So increasing the temperature will increase the force of the collisions and also the frequency, so thus increasing the pressure. Now, for the last coup de grace we have here, we have the combined gas law. So we can take all of these laws together and we can smush them all into what we call the master equation. Um, By a master equation, I mean like a master key. You know, how you don't need a bunch of different keys to open one door if you can just use one master key that will open all the doors, right? So this one will take care of everything. If the temperature remains constant, you just cover up the temperature. If the volume remains constant, you just cover up the volume. Pressure remains constant, cover up pressure. Okay? So, a container with an initial volume of 1 liter is the problem with these is you get a lot of numbers. So, let's go ahead and try to organize them. An initial volume, so was 1 liter, and occupied by gas at a pressure of 1.5 atmospheres at 225 degrees Celsius. So there's my temperature. And I'm going to have to add 273 to it to make it Kelvin. So that's going to be 2298 Kelvin. By changing the volume, okay, the pressure was increased to 6 atmospheres. So I don't think I know volume, but I do know pressure. So it's going to be 6 atmospheres. As the temperature is raised to 100 degrees Celsius. Sorry. And so we're going to add 273 to that, and it's going to be 373 Kelvin. What is the new volume in liters? Okay, so I put in liters, I'm going to get out liters. So really just plug and chug again. And so you have 1.5 your atmospheres. You're going to multiply that by your volume, 1.0 liters. We're going to divide it by 298 Kelvin. And we're going to get 6.0 atmospheres. And we're going to get X liters divided by 373 Kelvin. Okay. So now you will have to multiply by some kind of little creative fraction here. So I need to cancel out, need to get X by itself, right? So I need to get rid of this stuff. So to get rid of 373, I'm going to have to multiply by 373 on top. And to get rid of 6, I'm going to have to divide by 6 over here. So do the same thing to the other side. And so those go away. And what I'm left with is I will then just take in my calculator and watch me do this one. It's real fancy, guys. I'm going to take 373, multiply by 1.5, multiply by 1. I wonder if that'll do anything. And then I'm going to divide by 6, and then divide by 298. Remember, see how it's all in one line? And that works, okay? Hit the enter button, and there it is. There's my number, and that is my new volume. So that's going to be 0.31, and I'm going to round it 2 sig figs, looks like. Yeah, we're going to do 2 sig figs. That should be a decimal place there. So 0.31 liters. Okay. Now, example number 9, last one. A 700 milliliter gas sample at STP. Ooh, what does that mean? So the volume is 700 milliliters, and the pressure is at STP. So standard pressure is 1 atmosphere. Yeah, we want atmospheres. And the standard temperature is 273 Kelvin, or 0 degrees Celsius, right? But we don't want Celsius. We just want Kelvin. And the temperature is increased to 30 degrees Celsius. So it's compressed to the new volume. Sorry about that. New volume of 200 milliliters. I want to know the new pressure. and the new temperature is 30 plus 273. 30 plus 273 is going to be 303 Kelvin. Alrighty then. So we have 1 atmosphere times 700 milliliters divided by 273 Kelvin equals our X times 200 divided by 303 Kelvin. Okay, so we need to get rid of that stuff right there. We need to get rid of the 303 by multiplying by 303. We need to get rid of the 200 by dividing by 200. So those cancel out. And so we still have to multiply by 303 and divide by 200 over here. So now it's going to be 303 times 1 times 700 divided by 200 divided by 273, and that's going to give us 3.88 atmospheres. And that seems right. All right, thank y'all. Have a good day.